Question?
And those
What chapters will the test be over? Okay, guys, we're starting.
What sections specifically?
It'll be everything we've done this semester. It'll be up through chapter 10. Okay.
Just simple regression.
There will be a couple of questions of the more general stuff from the MA343 worksheet. So make sure that you look over what I passed back and what you got right. I haven't done it yet, but I will post the solutions to that. And it gives the solutions for every problem, not just the ones that you were assigned. So you can look through and see how you did. Some of you did them all and turned those in, but I only graded the ones that were assigned. So you can grade the others yourself. But then we did chapter 9 and chapter 10, right? Chapter 9 was the chi-square test, contingency table stuff. It includes the definition of relative risk, which we did, but that came out of chapter 8. But you don't really need to go back to chapter 8 to see it. It should be in your notes. But, yeah.
Is this test still on Monday?
The test will still be on Monday as long as I get through what I need to get through today. And I'm getting a little bit of a late start here, so we'll see how that goes. But
Are you uploading a review, or is it already up?
It's not up yet, but I will have a review, and I'll get it up this afternoon, and then we'll go over it on Friday. But I do reserve the right to maybe move this test to Wednesday because there is a lot left to do today. And one of my strategies for hurrying today was to just not make you responsible for some of the formulas. I don't like teaching that way, but in my notes, I've done it that way in the past for this class. And what I say is, if you want the formulas for how these things are computed, take MA346. Right? That's the regression class, and we do more detail there. So we won't go into as much theory here today, but...
Chapter 9 is just 9.1 and 9.2, right?
What's that?
Chapter 9 says 9.1 and 9.2.
Yes.
Yeah, there's only 2 sections to it. And this book is divided up into really short chapters, but some of them get fairly long.
It
So
looks like a ebook, but I think it's a special abomination of organization, so I couldn't tell for sure.
yeah, well. I want to... That ain't working. Well, let's go this way. Any questions over what we did last time? Kind of introduced you to linear regression and how to fit a linear regression model. Leanna, you may have to help me if that works. Okay, cool. Now I've ruined this slide, but we'll go back to there. One of the things that if I do that, yeah, good. So one of the things that I talked about last time was when you do a scatter plot, and you fit the line of best fit, then why is it called least fit? Do you remember that? I mean least squares. Why is it called the least squares method? Okay, so it minimizes, so MIN for minimize, the sum of squared residuals. Right? So the sum, I equal 1 to n, of the residuals. So what are residuals? How are they computed? Y minus y hat. So y, and I'm going to put a sub I on it, and what does the subscript indicate?
The ith number.
Okay. You said ith term, observation. I like that the ith observation. So think of having a spreadsheet, and each row is a different person, and you've measured 2 things about that person: their shoe size and their height. then the I subscript is the ith person. So it'll go to n, and n is always sample size, right? So the sum from 1 to n of yi minus y hat, right? And what is y hat? Predicted value. So you tell me somebody's shoe size, I can plug it into my linear regression equation and predict what their height would be. So then I look, well, what is their actual height? Subtract off what the model predicts, square it, and that's the sum of squared residuals. You want to minimize that. Now, I did not give you last time formulas for the slope and the intercept that come out of this. You may have, you may remember those formulas from MA343. If not, they are given in this book, but back in chapter 2, which is the MA343 part of this. But just for a little bit of refresher, B sub 1 is estimate of beta sub 1. Right? Remember, Greek letters means what?
Population parameter.
A population parameter. We estimate it with B1. Some books you'll see beta sub 1 with a hat over it. So estimate of beta 1. So a hat means predicted value or estimate. This book uses B1, and that's very common. Does anybody remember the formula for that? Okay, there's two forms of the formula. The one that he just gave is the only one I can ever remember. R times SY over SX. What is R? No, it doesn't stand for residual. It stands for correlation.
That's right. R.
Now, why correlation? Well, the Greek letter they use for correlation is rho. Starts with the R sound. So then they use R for the sample estimate of rho. Right? But other than that, there's not a good reason for the use of an R. But, so that's the correlation coefficient. And then SY and SX, what are those?
Standard deviation.
Standard deviation of the y variable, ignoring the x's. So come back to here. If I take each of these y's and I project it over here onto the y-axis, or each of these points, right? See what I'm doing? Blah, 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 blah. Then there is my variability in the y variable. If I put those y values into a list in my calculator and ask for the standard deviation of them, that's the SY. Then I do the same thing. I go down and put the x's down here. That variability is SX. So you take the ratio of the variability in your y variable over the variability of your x variable, multiply that by the correlation coefficient, and you get the slope of the regression line. There's a lot of algebra and even some calculus in there to derive that formula and to prove that it does minimize the sum of the squared residuals. You can use calculus. Remember how you minimize things in calculus?
I remember doing it.
You take a derivative, you set the derivative equal to 0, and solve. And what you come up with is this formula. This is the other form of the formula. I will not make you use this formula, but it's a good thing to at least see it and understand it. To me, formulas a lot of times are more to explain to me what's going on than to actually use as computation. The software will do this for us. Divided by the sum of x minus x bar quantity squared. So both of these sums are I equal 1 to n, just like the other one. Right? Now look at the top of this. What the heck we got going on there? Well, it's the sum of the cross products. How far is xi from its mean? So the x-coordinate of a point from its mean times the distance that the y-coordinate of that same point is from the y mean. So back to the graph. Here's a point right there. And that was a bad point to choose. Let's choose the one down here. There's a point, right? The regression line will always go through what point? I think I said this before. The regression line must go through the mean of the y's and the mean of the x. So it goes through the point x bar, y bar. So that point is x bar, y bar. Right? Now, this point, xi minus x bar, is that distance, horizontally back to the x bar mean. Take that distance, multiply by this distance, and that's this term on the top. Sum that across all of the subjects, and then divide by the thing on the bottom. What is this thing on the bottom doing? To answer that question, does it look like any formula you've seen before, or part of a formula you've seen before? The standard deviation of the x's. Remember, square root of that thing, and then divide by n minus 1. Right? So this is actually equivalent to s, dang it, sx squared times n minus 1. The thing you would divide that by, if I divide this by n minus 1, I would get sx squared. And then square root of it makes it sx, the standard deviation, right? So this thing on the bottom could be replaced with that. And I'll do that occasionally, interchange those two terms. They mean the same thing. So we call this the sum of the squares of the x's. Right? So this is sum of squares of the x's. This is sum of the cross products, x's and y's. So when you sum up all these cross products for every point, divide by the variability in the x's, you get the slope of the best fitting line. Right? And like I said, I'm not going to hold you to that formula. This one you should know. Right? So I might give you the correlation. Here's a set of data. The correlation is 0.68. The standard deviation of the y's is this. The standard deviation of the x's is this. What's the slope? So you should know that formula. Now once you have that formula, what's the formula for computing the intercept term? Y bar minus, I won't use beta 1. Technically, yes, it is beta 1, but we don't know beta 1, so we have to estimate it. Right? So once you compute the slope, you know the line goes through the point x bar, y bar, so basically you plug the coordinates of that point in and solve back for B0. You've got, remember, the equation of your regression line is y equal B0 plus B1x. Right? So all I'm doing is plugging in x bar, y bar, solving for B0 to get that. Right? So you find the slope first, use it to find the intercept. And that's going to be your line of best fit. The calculator gives it to you. Remember where we went when we did the MA343 review? Where did we go on our calculators to do a linear regression? Yeah, so on the TI 83 or 84 or something fancier, you're going to push the stat button. Oh wait, before you do that, you're going to put X into L1, a list. You have this list editor. And Y into L2. Then you push the stat button, go over to tests, and go down to lin reg. I'm not spelling very good here. t-test, yeah. It'll give you the slope, the intercept, and the correlation coefficient. It'll give you all three of those things. Okay? So, to answer your question, I may give you the correlation coefficient, I may have you compute it, whatever, but you need to be able to do this. And everybody in here has one of these calculators, so I don't feel guilty for making a test question that uses it. Okay, now let's talk about the inference that we make on a regression line. And remember that word inference, it means you're going to do a hypothesis test or a confidence interval. That's inference. Right? Well, about a regression line, you have I don't want the hat on it right now. This is one way that our book writes it out. In the population, any yi can be explained by this model. Right? So anybody's height, yi, is a linear function of their shoe size plus some random error. Right? Remember this?
Could you say that again? Please.
Which part?
Just what that means.
Okay. This is the response variable. So in my shoe size and height example, that's height. The subscript I means for the ith person. Right? So the height of the ith person can be thought of as a function of their shoe size. And it's a linear function. So this part right here is my linear relationship. Right? That's the equation of the line. But the point isn't going to fall exactly on the line, the actual point, so I add some random noise to that, random variability, to get above or below the line. What's this thing called?
Error.
The error term, or residual. Right? Epsilon I is estimated by EI, the sample residual. Right? And it's exactly the same equation, except it's got a lowercase b0, a lowercase b1, and an EI instead of an epsilon I. So in other words, we're trying to do this, but we don't know the whole population, so we took a sample, and so this is the sample residual. Right? So if we go back to a graph, this distance from any point to the line is E sub I, the residual. And that's this yi minus yi hat. Okay? So, sum of squares, sum of squared residuals. Right? We talked about that's what this is doing. We're minimizing the sum of the squared residuals. So this term here, sum of squared residuals, I can say is equal to sum I equal 1 to n of EI squared. Right? Now, in this formula, I said this thing on the bottom was the sum of the squares of the x's. And if I divide that by n minus 1, I get the variance of the x's. And then square root, I get the estimate of the standard deviation, the standard amount of variability in the x's. Well, one thing that's of interest in a regression model is a third parameter. In this model, I have two parameters listed here. I have the intercept parameter, the slope parameter, but this is a random error term. And what is of interest sometimes is what's the variability of that random variable. Right? So we want to know sigma squared sub epsilon. That's the variance of epsilon sub I. Yeah.
Back to this, the lowercase, the observed error. You said it turns something else up there into lowercase. Which parts of that formula were then termed lowercase?
Not necessarily lowercase, but instead of Greek letters,
Wrote the Greek letters.
instead of Greek letters, we replaced that with lowercase regular letters,
That's what I missed.
and we have the sample version of it, right? So this E sub I is all we're ever going to see. We don't get to see the epsilon sub I's because we never know what the true regression equation is, right? But think of subtracting this epsilon I from both sides. Then I got y sub I minus epsilon I, right? The observed value minus the residual, that should get me to the line. Okay? So this sigma squared sub epsilon, and the book doesn't put the sub epsilon on it, it just says sigma squared, is the variability of the residuals. Now I gave you last time 4 assumptions about regression models, and one of them dealt with the variance of those residuals. Do you remember what it said? The variance around the regression equation has to be constant. Okay? So if I do a residual plot, I take the residuals and I plot them, I'll get some positives, I'll get some negatives. Right? In fact, magnitude-wise, you'll have an equal magnitude of positives and negatives. You might have more of one, but if you have a really big positive, you might have 3 small negatives that offset that. Right? If that assumption is met about the variance of the epsilons, then you would expect to see what in your residual plot? Remember, you get a residual for every subject or every observation in your data set. Right? And if I plot those residuals, what should it look like? And usually you have to pick an x-axis variable, and you can get different residual plots that do it different, but the most common is to have your x variable, right? So think of shoe size 4, 5, 6, up to 18 or whatever, right? What would that residual plot look like? Okay, it should look straight across. It should be something like, I made some dashes on accident, but, right? That is constant variance. The variability around the line is staying constant. Question?
And there's the same amount of number on the bottom and the top?
Roughly. Not exactly the same, but the same magnitude, right? If you sum the residuals without squaring them, what do they sum to? 0. So if I have a really big positive one, I might have, like I have a positive 3, I might have a -1, a -1, and a -1 that would sum it out. They always sum to 0. That's why we have to square them. Okay, now, draw me a picture where you do not meet the assumption of a constant variance. How would I change this picture?
Make it parabolic or any shape that's not straight across.
Okay, if I start selectively erasing some points, and then I'm going to add some more points to make this more obvious. You see a trend in the residuals, right? That tells you, ooh, my x variable didn't explain everything, right? From the model right here, if the linear part of this explains everything that can be explained, the only thing left are random noise, random error terms, then it should look like random scatter. But if you see a pattern in the residuals of any kind, a parabolic shape, a line like I drew because it was easier than a parabolic shape, whatever, then that tells you, hey, your X did not fully explain the relationship with X. There's something missing, right? But what about this? Let me use my eraser again. And what do you see going on there?
The higher X gets, the greater the variability is.
As X gets bigger, the variability gets bigger, right? You've got a funnel shape to the residual plot.
So it's less accurate with the
That's
higher
exactly right.
shoe size.
Your model is not predicting as well for big shoe sizes, right? There's more variability in height for people with big feet than there is for people with little feet. That's not actually the case for that scenario, but a lot of regression models might look like this. So any kind of a fanning out or a funneling in or whatever, that's non-constant variance, right? If you see patterns in the residual like that, really any pattern at all, then you think, oh, maybe my inference that I make from this is not going to be valid. Okay? So now let's talk about that inference. The first thing we might want to make inference about is the parameters. So the parameter beta 1 is the slope parameter. I may want to know, okay, I know that slope is not going to be perfectly correct, but how close is it? Give me a confidence interval for the slope. Well, in order to put a confidence interval on slope, we need to have an idea of the standard error of the slope. Right? Let me see if I can get this up reasonably quick. Last time I ran...
Is that R the same as just the R, like the R we dealt with in regression, like the R squared, like square rooted? R squared. I know, but that, cause my calculator, that when I do the t-test, it just gives me R and R squared. Those just look like the explain versus unexplained.
R is correlation coefficient, and R squared, what is R squared?
What's the amount of the percent of reduction or the variability?
Okay, good.
Model.
You can say that in an equivalent way by saying it's the percent of the variability in the y variable that can be explained by the x variable. Right? So those two mean the same things. Let me hunt here for a little bit. I thought I put this into a PowerPoint presentation. I apologize. I thought I... Does anybody see the PowerPoint icon usually shows up, and that's what I'm scanning for, but what I want to show is an example from the shoe size height by semester, and SAS is just not working very well, so I was hoping... Nope, not there. Let me look in a previous semester. Maybe I put it in there. Well, that's not working, so... rather than waste more time on it, I'm going to draw for you what I was trying to pull up. I have it prepared in a slideshow, but I showed you last time a scatter plot that has all the 10,000 observations from all my semesters together. Well, if I fit a separate regression line for every semester's worth of data, right? It's interesting what that ends up looking like. It ends up basically like I'm way exaggerating here, but across all those semesters, so I have about 20 different semesters worth of data. So I have 20 different regression lines. They don't, any of them have exactly the same slope. So they tilt a little bit. They don't all go through the same X bar, Y bar because they're each set separate. So it's the X bar, Y bar from that particular semester. But it turns out that they're all really close to each other. So they kind of go through this point near the middle. So different slope means it tilts around that point, right? So if it tilts, that means there's variability in those B1 estimates from semester to semester, or from sample to sample to sample. So B1 is a random variable. Oh, that's a term from MA343. What's a random variable? Emily, I'm shocked you're not giving me the answer to this. It's my favorite definition in MA343. A random variable is a variable that's random.
I was going to say that, but I thought you'd yell at me.
It's a variable that's random, which means it has a probability distribution. What's random about the slope? Who'd you get in your sample? That's what's random. If you took a random sample, then the slope you get is going to be different than another random sample because you got different people in it, right? So it has variability. Well, it turns out, we don't do that in this class, but B1 is normal, right? It's a normally distributed random variable. It'll be centered, that distribution is centered at the population slope. Hey, that's good. That means it's an unbiased estimate of the population slope. But what's the variability of it? Right? So the variance of B1, we need to know that.
You said it's centered at the what slope?
At the population slope. At the betas. So remember this notation, capital N for normal, mean, variance. So the mean of all of the possible B1s you could get, they'll be centered at the population thing you're trying to estimate. If we knew this variability, then we could use it to form confidence intervals around that beta 1. Okay? So the standard error of B1 is the square root of sigma squared sub B1, right? So standard error, you'll see me use this a lot more than this, but a lot of times we just write it as sigma B1 with no square on it, same thing, but I tend to use this notation, and so does the book, because you can read it, SE, standard error of B1, okay? So the standard error of B1 is equal to S sub E divided by the sum of the squares of the X variable around its mean. So that's not a real convenient way to write it. So algebraically equivalent is SE times N minus 1 SX squared. Let me find that formula in the book so I can point you to a page, and I'm going to start kind of bailing out and just giving you the I'm sorry. This should all be under a square root. All right. So then this is under a square root as well. So that can be written as SE over square root of n minus 1 times SX, the standard deviation of the x's. Now, again, the reason I'm giving you formulas isn't so much for you to have something to memorize, but it helps to figure out, well, what's going on here? If I want to know variability in the slope, what affects the variability in the slope? Well, what's on top of the fraction? Standard error of the estimate is called sometimes, or the standard error of the regression. So that's the variability in the residuals. If that number's big, there's a lot of variability in the residuals, the points are really scattered around the line, then this will be big. It means you're not going to have much confidence in the slope you got from it, right? But if they're really tight around the line, you get very small residuals, then this will be a small number. But what happens when you put Sx on the bottom of the fraction? A lot of variability in the x variable does what? It shrinks it. Why would that? I don't understand that. Why? Yeah, let me go here and make a new page. Let's draw a scatter plot. Tell me the slope of the best fitting line.
Somewhere like that.
Well, I got very little variability in the x direction. This is my x variable. Almost all of my points came from the same shoe size. Think of it that way, right? Okay, you want me to get more variability in my x's? So I'll get some x's and I spread them out. Now it's a lot easier to estimate the slope, right? You get less error when you try to estimate the slope if you get a wide range of x's than if you don't. If you get a really small amount of variability in the x's, then it's hard to estimate the slope. So this formula shows that. Take the variability in the x's as the denominator, then you take the variability in your residuals, you divide out the amount of spread you have in the x direction. Right? So if this B1 is normally distributed, it's basically a mean, isn't it? We're trying to estimate a mean of the population. So how do you make confidence intervals for means from a population? We just did that. MA343 review. If I ask you to give a confidence interval for a mean, where'd you go on your calculator? Okay, 1 samp t int. Right? It's a t. That's the point. It's normally distributed, but since we have to estimate the variance, it becomes a t distribution. And that discussion happened in MA343, so I won't repeat it. But the point is to put a confidence interval around our sample estimate to give me a confidence interval estimate of a population parameter, you're going to use a t distribution. And it's just like what you're used to. So a confidence interval for beta 1 is B1, that's the sample estimate of beta 1, plus and minus a t critical value times the standard error of B1. And all confidence intervals are like that. You start with a point estimate from your sample. You add and subtract a critical value times the standard error of that point estimate. Got it? So the only thing we're left to figure out is what are the degrees of freedom. for that T critical value? Well, the degrees of freedom are n minus 2. When you did confidence intervals for a mean from a sample, it was n minus 1, right? Well, the 2, think of it as being the number of parameters that have to be estimated. When you're estimating mean from a sample, you're estimating one thing, mu. Here, I have to estimate not only the slope, but I also have to estimate the intercept of that line. So I'm estimating 2 parameters, so I lose 1 degree of freedom for each of those parameters being estimated. So you got n minus 2 degrees of freedom. So if your sample is 30, you're going to have 28 degrees of freedom. Right? So then you can get your T critical value from a T table or from your inverse T function on your calculator. Okay? All right, let me... I just run us out of time. I wanted to show some output, and luckily from... I don't know if I can make this bigger for that screen. Oh, yeah, I can. Good. So this is the bottom part of the model, and it has parameter estimate and standard error. Right? And then I ask for 95% confidence limits on that parameter. That's what we just showed. The software, and you can do this in Excel or in SAS, the software will produce a standard error of each of the parameters. So this is this number 316.36 is B0, 19.86 is B1. They each have their own standard error. They each have then their own confidence interval. Okay? So next time, we'll finish this section. So we're not going to get to the test by Monday. Let's move the test back to next Wednesday. We'll finish 10-2 on Friday, and then we'll review on Monday. All right? We will see you Friday. Yep.
Look at